Have you ever really stopped to think about how you make a choice? I don't just mean the big life-changing ones, but the millions of little, tiny decisions you make every single day. You know, from deciding to hit the snooze button to slamming on the brakes in traffic. It all boils down to this incredible lightning-fast computation happening inside your head. So today, we're gonna peek under the hood and figure out how that 3-pound universe between your ears goes from just seeing the world to actually making a call.
Seriously, think about it. You're driving, right? A car suddenly swerves into your lane, and in less than a heartbeat, you've seen it, processed the danger, and your foot is already moving to the brake. It feels totally automatic, almost magical. But it's not magic. It's a super precise, high-stakes calculation performed by your neurons. So the big question is, how on earth does the brain actually pull that off?
Okay, so let's break this down. At its absolute core, any decision you make, whether it's simple or life-saving, really has two main jobs. First, your brain has to gather the facts. We'll call this the evidence. It's the raw sensory information, the brain basically asking itself, okay, what am I actually seeing right now? And second, it has to weigh all that evidence to come to some kind of conclusion. That's the process. It's the deliberation part that answers the question, all right, given what I'm seeing, what should I do about it? We're going to tackle both of these, starting with how the brain gets its evidence in the first place.
Right, so let's get into part one, gathering the evidence. How does your brain take this chaotic flood of light hitting your eyeballs and turn it into something that actually makes sense? To figure that out, we have to go right to the very beginning, to the first stage of visual processing in the cortex.
You know, it's funny to think about now, but back in the 1950s, scientists knew a little bit about how the cells in our retinas worked. They were basically simple little detectors for spots of light. But the visual cortex, the part of the brain that does all the heavy lifting for seeing, was a complete and total mystery. It was a black box. And these two researchers, David Hubel and Torsten Wiesel, they were determined to pry it open.
To do this, they used this really critical idea called a receptive field. The best way to think about it is like a single neuron's personal little window onto the world. It's the specific patch of your vision that it's in charge of watching. Now, they already knew that retinal cells liked simple circular spots of light. But when they tried showing those same spots to neurons in the cortex, they got crickets, almost nothing. The cortex was clearly playing a totally different, way more sophisticated game. The story of their big breakthrough is actually kind of legendary. Hubel and Wiesel were showing all sorts of patterns to this anesthetized cat, and they were getting just nothing. Super weak responses. Then, totally by accident, as they were sliding a new glass slide into their projector, the sharp edge of the slide cast this thin line of light across the screen. And all of a sudden, a neuron just went nuts, firing like a machine gun. That was the aha moment. The key wasn't a spot of light, it was a simple bar of light. And, this is crucial, it had to be at the absolute 100% perfect angle.
So why was the angle so important? Well, this is the brilliant mechanism they figured out. Unlike those simple cells in the retina, these cortical neurons have receptive fields with an excitatory on area right next to an inhibitory off area. So when a bar of light lines up perfectly with that on zone, it gets the whole thing excited at once while completely missing the off zone. The result is a massive signal. But if you tilt that bar just a little bit, it starts to hit that inhibitory off zone, which actively shuts the signal down. It's this incredibly precise filtering system.
And this finding, which they summed up in their 1959 paper, was a complete game changer. It showed that the cortex isn't just taking a passive photo of the world. No, it's actively breaking it down into its component parts. These neurons are feature detectors, specifically tuned for lines and edges. And this idea laid the foundation for a whole hierarchical model of vision, where you combine simple features like lines to build more complex shapes. It's an idea, by the way, that directly inspired the layered architecture of the deep neural networks we use today.
So this brings up a really deep question about how the brain is designed. I mean, why go to all this trouble? Why would evolution build a brain that's packed with millions of these little specialized edge detectors, each one tuned to a slightly different angle? What's the point of this super-structured, almost crystalline organization?
Well, the answer is pretty profound. In the natural world, edges are everything. Objects are defined by their boundaries. Recognizing a predator hiding in the grass or a piece of fruit hanging from a tree, it all starts with spotting its edges. So by having this massive army of specialized neurons, the brain can instantly deconstruct any complex scene into a set of simple lines and orientations. This is the very first absolutely essential step in gathering evidence, turning visual chaos into structured, useful information.
Okay, so the brain has its evidence. The world has been broken down into a bunch of edges and motion. But you know, evidence is pretty useless if you don't do anything with it.
So that brings us to the second and super crucial part of our story. How does the brain take that evidence and actually weigh it to make a choice? To get this, we need a really cool concept from researchers like Michael Shadlin and Joshua Gold, the decision variable. The best way to picture this is as the brain's internal running score. So as each new piece of evidence comes in from those edge-detecting neurons we just talked about, the score for one option, let's say the car is moving left, goes up a little. The score for the other option goes down. This variable isn't the evidence itself, it's the state of deliberation about the evidence. It's the process of thinking. You can think of this whole process as a kind of random walk. Imagine the decision variable starting at 0, right in the middle. A piece of evidence for choice A comes in and gives it a little nudge up. A piece for choice B nudges it down. So it just sort of drifts and wanders, adding up information moment by moment. The decision isn't actually made until this drifting score finally smacks into a preset finish line or a decision boundary, and that is the point of no return. That's the moment of commitment.
And what's so cool is that this model perfectly explains something we all deal with every day, the speed-accuracy trade-off. Think about it. If you set that decision boundary really high, you're going to need a ton of evidence to reach it. Your decisions will be slow and careful, but you'll probably get them right. On the other hand, if you're in a hurry, you can lower that boundary. You'll make a choice way faster, but you're doing it with less evidence, which means you're more likely to make a mistake. This bounded accumulation is just so clever because it guarantees a decision is always made. It stops the brain from getting stuck thinking forever.
So this whole evidence accumulation model, it sounds elegant, it sounds smart, but is it really what's going on inside our brains? To find out, researchers came up with this brilliant experiment to literally watch a decision happen in real time at the level of individual brain cells.
Okay, so the experiment is called the random dot motion task. A monkey looks at a screen of swirling dots and just has to decide which way they're generally moving. To explain how the brain does this, let's use a courthouse analogy. First, you've got a brain area called MT. MT is the expert witness. It's sensitive to motion, so it provides the raw moment-by-moment testimony about which way the dots seem to be going. Then you've got area LIP. LIP is the jury. It doesn't see the dots itself. It just listens to the evidence from the witness, MT, and adds it all up over time to reach a final verdict.
So here's the million-dollar question. If area LIP is our neural jury, what should its deliberation actually look like? If we could listen in on the chatter of those LIP neurons while the monkey is weighing the evidence, what would we expect to hear? And what they found was just perfect. The firing rate of an LIP neuron that, say, prefers a rightward choice gradually ramps up as evidence for rightward motion pours in from MT. And get this, if the evidence is really strong and clear, that ramp is super steep and the decision is fast. If the evidence is weak and ambiguous, the ramp is shallow and the decision is slow. But here's the kicker. The monkey makes its move at the exact moment the neuron's firing rate hits a consistent, fixed threshold. This is the smoking gun. It's the physical proof of that decision variable we were talking about, right there in the brain.
Now, to completely seal the deal, they used a technique called microstimulation. It's like giving specific neurons a tiny electrical nudge. And this is so cool. When they stimulated the witness's area MT, it was like slipping the jury more convincing evidence. The monkey became way more likely to choose that direction because the slope of that ramp in LIP got steeper. But stimulating the jury, area LIP, was different. That didn't change the evidence. Instead, it was like giving the jury a head start, a little bias that moved the starting point of the ramp closer to the finish line. This just elegantly proved that MT provides the evidence, and LIP is the one that adds it all up.
All right, let's pull all these threads together. We've seen the two main acts in the brain's decision-making play. First, gathering all the clues, and second, weighing those clues to reach a verdict. What these absolutely landmark studies show us is this beautifully simple, yet really profound, two-step process. First, just like Hubel and Wiesel discovered, the brain acts like a detective. It breaks down this messy visual world into fundamental clues, simple things like lines, edges, and motion. That's step one, gather the evidence. Then, as Gold and Shadlin showed, the brain acts as a jury. It patiently adds up all those clues over time until the weight of the evidence is just strong enough to cross a boundary and deliver a verdict. That's step two, the decision itself.
And this leaves us with a really fascinating and maybe kind of unsettling final thought. If a decision is literally the physical outcome of a race between groups of neurons to a fixed finish line, what does that say about our conscious experience of making a choice? It suggests that the feeling of deliberation, of weighing your options, even your sense of confidence, it might just be the brain's awareness of this underlying neural competition.
It's a question that connects the nuts and bolts of how neurons fire to the biggest philosophical mysteries of who we are.